Hey guys, apologies for my absence the other day, and just wanted to go through a couple of things about the slides that we did, and hopefully this can help you with answering some of these questions. So the first thing we're going to do is question number 1. A student performed a gravimetric analysis. This just means a mass analysis to determine the percentage of Ag by mass in an alloy. An alloy is going to be a mixture of usually two metals, and in this case Ag, silver, and Cu, copper. A sample of alloy was dissolved completely in a solution of HNO3, forming aqueous ions Ag+ and Cu2+. An excess amount of NaCl, this is added to the solution, causing the formation of a precipitate. And in this case, precipitate means a solid product. AgCl in this case. So AgCl is formed. The student collects the precipitate, the solid product, by filtration. This is a method used to separate liquid and solid. Dries it, so removes all of the water content, and records its mass. Data is shown below. So we have the original alloy here, 2 grams, and we have 0.72 grams of the precipitate. So, to begin, what are we going to do is we're going to record the molecular mass, the MR, of AgCl, which is going to be equal to silver's 107.9 plus chlorine 35.5. And in this case, I've gone for about 3 significant figures here and 4 significant figures here. According to the periodic table, you could use 108. It shouldn't make too much of a difference. So this should give us a total of 143.3, around about, or 143.4. In this case, we're going to do one mass calculation into moles, so 0.72 grams from our mass of precipitate, multiplied by 1 over 143.3. And this is going to give us a molar value. So this is going to be the grams divided by the molecular mass, and this should give us the number of moles of AgCl. Now, as you know, in AgCl, we have a 1-to-1 ratio of Ag, and in AgCl, there is 1 mole of silver for 1 mole of silver chloride. So in this case, all we need to do is multiply this number by the molar mass of silver, which is going to be 107.9, and this should give us our mass of silver in our compound, which is going to be around about 0.54. Just note here, I say 143.3 because I'm using 107.87 and this number here 35.45 as exact value. So this is more of an exact value, not this number here. So just be aware, this number is 143.3 or 143.4. So now we have the mass of silver. We can just do a mass percentage. So we need to find the percentage of Ag in the alloy, which is going to be 0.54 divided by the total mass, which is going to be 2.00, and that should warrant us about 0.27. Of course, with percentages, we just need to multiply it by 100, so we get 0.27 times 100, and that gives us 27% by mass. So the answer here is going to be A. Okay, and for question 2, what we're going to do is, let's read the question first. So, mass percent of potassium in pure K2SO4 potassium sulfate is about 45%. A chemist analyzes an impure sample of K2SO4 and determines that the mass percent of potassium is 50%. Which of the following impurities could account for the high mass percent of potassium in this sample? Okay, so for this question, we can calculate the original intended percent by using our molecular mass percentage formula. So we can say the mass percent of K2 or K in K2SO4 is going to be around about 78.2, which comes from our 2 times 39.1. This is going to be the molecular mass of K, of potassium, because there's 2 potassiums in K2SO4. So we have 78.2 divided by the total mass, which is going to be 78.2 plus 32.06, also 32.0 is fine, plus 64.0. And this should give us a percentage of around about 0.45 or 45%. So this is correct. We know that this first one is a pure sample. We didn't need to do this, but for the fact of explaining, it should make life a little bit easier. So this question is asking, why is it increasing in percentage when this should be 45%? So if any of these are added, they should increase the mass percent of potassium. So that means the mass percent should be higher than 45%. So around about 50%, or maybe even more. And to do this, we can do this one by one, which I will do, and then explain it towards the end. So the first thing we're going to do is find the mass percentage of KBr, which is potassium bromide. This is going to be taking our 39.1 divided by the total mass, 39.1, plus bromine, which is going to be 79.9. And this gives us a mass percentage of around about 33%, which is lower. So from this one we can say that A is incorrect. B, potassium iodide, is going to be the same calculation, so 39.1 divided by 39.1 plus iodine, which is 129.9, and this should give us a percentage of around about 24%. I'm just going to put the percentages here just to make life a little bit easier. So 25% or 24% is less than 45, less than 50 certainly, so it's not going to be Ki, potassium iodide. KCN is going to be 39.1 divided by 39.1 plus 12.1, or 12.001 plus 14.0, and this is going to give us a percentage of around about 60%. So this seems to be most likely, although I will go on to the KMnO4 just to double check. So potassium manganate is going to be 39, sorry I'm using my periodic table here as well, divided by 39.1 plus 54.9, sorry, plus 64. And this is going to be about 25%. So this is less than 45% as well. So in order to bring up the percentage, the only valid option is going to be the 60% here. So potassium cyanide is going to be the option which brings up that 45% to around about 50%. If you're talking in terms of average, 45%, and then you add some potassium cyanide, which is 60% by mass, you get an average of around about 50%. It averages out into the middle, which makes sense for this question. For our last question here, question 3, I'm just going to read it out again. So a mixture, again, this is a mixture, not a compound. So the mixture means it has not chemically reacted with each other. It's a mixture of lithium chloride, which is LiCl, and NaCl, which is going to be sodium chloride. And it's analysed to find a 5% lithium by mass. Which of the following represents the best mass percent of LiCl in the mixture? So this question's asking us not just LiCl, but also NaCl, which can be a little bit confusing. But let's start off by looking at the percentage of 5%. In fact, before we go on to the 5%, what I'd like to do is in fact just look at the molar mass to confirm what 100% solution would be. So in this case, we have the mass percent of lithium in pure LiCl, lithium chloride, is going to be, using our periodic table, about 6.9 divided by the molar mass of LiCl, which is going to be 6.9 plus 35.5, and this should give us a percentage of around about 0.164, let's say 164. I have done these calculations prior to this using exact numbers as well, so this should be equal to about 16%, let's say 16% or 16.4. This is 100% lithium chloride, So in this mixture, if we have 100% lithium chloride, then it should be 16.4% lithium. However, in this example, we have only 5% lithium in lithium chloride and NaCl. So what we're trying to do is we're trying to find what the multiplier has been to the 16%. So we're going to define that multiplier as x times by 16.4 our mass percent of lithium in lithium chloride, which has been essentially diluted by something, in this case sodium chloride, and we can solve for x. X in this case is a multiplier of 0.305, which is going to be, as a percentage, 30.5%. Now this is the answer B, which is correct. So what can we determine from this is that the rest of this mixture, which is going to be 69.5%, is going to be NaCl. The lithium chloride has been diluted, I say diluted, but it's been mixed with sodium chloride to reduce the amount of 16% lithium down to 5% lithium. And from that, 5% has been multiplied by 30.5% to get the 16.4% percentage. So the answer is going to be 30.5%. The rest of this is going to be sodium chloride. Let's write that down. 69.5% of solution SLN is NaCl. Hopefully that helps. Okay, so for the last part then, just going to go through the couple of parts until the quantum numbers section. So this can get a little bit confusing, but I'll try to explain it as in much detail as possible. So to start off with, properties of the atomic model that predated the Bohr model. An atom is composed of very small, positively charged nucleus containing neutrons and protons. We remember this from Unit 1, and even smaller, negatively charged electrons outside of the nucleus. The electrons and the nucleus are attracted to each other since they have opposite charges. The electrons are free to move in almost empty space of the atom. And you've probably seen this before in some diagrams that look like this, where you have the nucleus here, which is full of zero charged nucleons, neutrons, and positively charged nucleons as protons. And around the edge you've probably seen X's drawn as electrons in an atom. Moving on, we can say that atoms are stable and they don't collapse. This is not something we're going to look at just yet in AP. This is more of a precursor to what's going to be discussed in around about Unit 3, 3.6 to 3.8. But I thought I'd include it to help you out with the understanding that atoms don't disintegrate, they don't go anywhere. The second part is that atoms don't spontaneously emit light all of the time. They only emit light at certain times. If they did, then it would be observed. In this case, it's not observed, so we can say that they don't emit light most of the time. Again, we can move this onto section 3 here. When they do emit light, it consists of only specific colors, which are going to be in our spectrum. If you're doing AP Physics 2, you'll be looking at this as well. This is called emission, electron emission, and in AP Chemistry, this should be, I believe it's going to be unit 3.8, which we'll be looking at. Originally, I did include some information about 3.8 or 3.6. I can't remember where it was. But if you're interested to read about the emission spectrum, you can see that they change in energy levels. So when something's dropping energy levels, you get some emission, etc. And you get colors which are emitted from photons being emitted from different atomic processes. And only narrow lines of colors are observed in a continuous spectrum. So this is the visible light spectrum on the electromagnetic spectrum. Niels Bohr is the person who decided to draw an atom. Here he is. And he said that it should look like this, where we have different levels which are denoted as n. N equals 1 is going to be called the ground state. And it goes up and up and up for every energy level that you have. So to find the permitted electron orbits around the nucleus, electrons could orbit the nucleus like planets, and that's going to be really important later. Like they orbit the sun. They're only permitted, but only at permitted radii. So these radii are the distance from the nucleus to the energy level. They increase in proportion to n squared, so orbits get much larger as n increases. So that means it starts off small and then increases at a square number. And we'll take a look at that during something which is called Coulomb's law. And that's later on in this class. So the next part is going to be talking about energy levels in a bit more detail. So these are called energy levels. And electrons can absorb energy, and they can also they can be represented in energy levels n equals 1, n equals 2, n equals 3, n equals 4, and keep on going. This is just a fundamental drawing, and I'm sure you've probably seen this before drawing in your previous lessons in chemistry. This is a really basic drawing though of what Niels Bohr said. So we have energy levels, and later on in the course we'll explain these using something called orbitals. Electrons are on each of these energy levels. Now, to get a little bit more in depth, we can start to say that increasing the size of atomic radii, orbitals radii, at high energy levels, we expect atomic size to increase as the period increases. This is interesting to say, and we'll take a look at this in a minute. Due to the higher effective nuclear charge when moving from left to right across the period, we would expect the atomic size to decrease when we are moving across a period. So this is going to be proved again using Coulomb's law. This part here shows us the atomic radii compared to our rows, which are going to be going along the periodic table, and our groups as well. Groups are going to be going down, and rows are going to be going across, and sometimes rows are going to be called periods as well. So period 1, period 2, period 3. This one's going to be period 2 here, this one's period 3. So group 1, if you look at your periodic table, you might notice that some of these groups are labelled 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, etc. Some of them skip a little bit. That's because these groups go from group 1 and 2, and then they miss the transition metals and go to group 13, which is going to be here. So the reason why these are getting smaller is because of a force of attraction between the nucleus and the valence electrons, and that's really important to realize. So this is the trend so far. So the size is determined by what in AP we call the Coulomb's law, and if again you're studying AP Physics 2, you're going to be looking at this in terms of something with a K in front of it, which is going to be the force of attraction between two particles. Q is going to be the charge of one subatomic particle. And then you have Q2, which is also going to be a charge of a subatomic particle. So it's going to be effectively Q, which is going to be the charge of an electron, or I should actually say minus Q, times by Q, which is going to be the charge of a proton. In this case, this gives us Q squared. Don't need to worry about the minus here. In fact, in AP chemistry, all we're looking at is actually the proportionality between the force of attraction and the relationship of Q times Q divided by R squared. And remember from last time we said that the radii is going to increase at a square. So the charge of a electron times by the charge of a proton is going to give us Q squared. And this is going to be proportional to the force of attraction between two parts of an atom. A stronger attractive force pulls the electrons closer to the nucleus, and this results in a smaller distance, a smaller atomic radii. Something that's really important here as well that we need to consider is that these electrons are going to only be something we call valence electrons, which is the outer electrons. And this is explained by something called shielding. And shielding is going to be something we look at during our orbital mechanics when we're looking at how different electrons fall into orbitals. One proton, for example, 1q in hydrogen is attracted to one outer electron, 1q. So this again could be minus q to result in q squared. So the force of hydrogen is going to be 1f, which is going to be equated to q times q squared. In helium, we have two protons, and they're attracted to two outer electrons. So it's going to be 2q times by 2q, which is going to give us 2q squared. And this is proportional to 2f. Sorry, my apologies for the last section. I thought I made a mistake, but I actually didn't. Well, I did here. As you know, excuse me, 2q times by 2q is not going to be 2q. I was wondering why there's a mistake here. This should actually be 4q squared. Sorry, when I wrote this, I was thinking about another element. In this case, this should be 4q squared, which is proportional to, and again, I'm just testing you. You can make sense of this. It's equal to 4f. So this is going to be 4q squared. There are 2 electrons in the outer shell, indeed, not just 1. So this should be 2 outer electrons. My apologies. I wrote this in a little bit of a haste, so there's a slight mistake there. So 4q squared, which is proportional to 4f. And this larger force attracts the electrons closer to the nucleus. And okay, so we're going to look at shielding now. And shielding is where we have core electrons which are being shielded by repulsion from valence electrons. So shielding is a term used to define when core inner electrons repel outer electrons and are not given a force of attraction by protons in the nucleus. So in an element such as silicon, you could imagine it being, sorry, not 14 q squared, it should be 14 squared. You can imagine it being a huge number because you have 14 electrons and 14 protons. However, this is not correct. It will only result in, again, this is a mistake here, a small mistake, which is going to be 16q squared. This is because 10 protons in the nucleus have cancelled out effectively 10 core electrons which are around the outside. So we have the core electrons which are being attracted by the protons in the center, and the ones which are important in Coulomb's law is going to be the valence electrons, which are going to be the ones on the outside. Again, apologies for the mistakes here, just a couple of errors. Yeah, these numbers are going to be much larger here, and this number here is going to be 16q squared. So this is because we have 4 valence electrons in silicon and we have 4 protons which aren't being affected by shielding. So this is going to result in 4 multiplied by 4 times by q, which gives us 16q squared. So when we start to look at atoms in equal numbers of protons and electrons, we can start to make sense of ionization a little bit more as well. And this means that we can say that if we have 12 protons, then we can have 12 electrons, then we have a net charge of 0, because they have all cancelled each other out. So this magnesium atom just naturally occurring is going to be not an ion, it's just going to be a metallic element. And this is where it starts to get into talking about ionization. Ionization is the amount of energy required to remove an electron from the outer shell, which is going to be the valence electron. And this requires energy to do this. This energy is going to be called the first ionization energy. We'll look at that in a second. But to look at the maths, if you have 12 protons and then you have now 11 electrons, you now have a charge of +1. So this is going to now be called Mg+, and this is an ion. Specifically, it's going to be called a cation. So a cation is a positively charged ion. The first ionization energy is going to be the amount of energy needed to remove that first electron. And then subsequently, the second ionization energy is the amount of energy that you need to put into the atom to remove the second electron. There are ways you can put in energy to electrons. You can use heat. You can use other electrons. In this case, in AP chemistry, we don't need to know how to do it. We just need to know that there is an amount of energy which is put into an electron to remove that electron from the atom. So in this case, we can remove 2 electrons from Mg to get 2E-. We can then apply Coulomb's law to see which one is held together more tightly. So applying Coulomb's law helps us to understand how our ionization energy changes through elements. In this case, we have the force of attraction between the valence electrons here and the force of the valence electrons here. So which one's held more tightly? Well, in lithium, these numbers are done for you, and in beryllium it's done for you. So Ke squared and 2Ke squared, the force of attraction is going to be 2 times as much in beryllium. This means that if there's a stronger force of attraction between the nucleus and the electron, then it's going to take more force to remove it, which means that beryllium is going to be the more strongly attracted atom. If it's the more strongly attracted atom, then it's going to require more energy to remove that electron, from the atom. This means that the first ionization energy is going to be higher for beryllium than lithium. And this applies across the periodic table. We can say that as the force increases, the atom holds onto the electrons tighter. It will require more energy, which is ionization energy, to take them away. As the force increases, therefore we can say increases as well. Sorry, my camera just switched to my light there. So, some questions. How does Coulomb's law affect radius size? How will Coulomb's law affect ionization energy? How will the trend in atomic size relate to the trend in ionization? Well, if you increase the force, then you're going to decrease the radius because it's inversely proportional to the square. How will Coulomb's law affect the ionization energy? A higher force means a higher energy. And how will the trend in atomic size relate to the trend in ionization energy? Well, as you get a smaller atom, the ionization energy is going to increase. And this is described in this part here as the electrical attraction between the nucleus and outer atoms, electrons, increases. The atomic radius decreases. The ionization energy increases. This is what we just said here. The trend of atomic radius and the ionization energy have an inverse relationship. So one goes up, the radius goes up, the ionization energy goes down. Atomic radius increases when going down the periodic table because there's more energy levels. And of course, when you're going across it, because there's going to be higher force of attraction. Ionization energy decreases when moving down the periodic table because it gets bigger, and moving to the right because of the force of attraction. Finally, we can have a look at this. This is a common concept in AP chemistry, where we're given a couple of elements and we're told which one has the highest ionization energies. Well, you can look at Coulomb's law, whether it's due to radius or whether it's due to the amount of valence electrons. Magnesium is going to have 2, which is going to be 2F. Aluminium has 3F. Silicon is proportional to 4F. So the strongest force of attraction is silicon, therefore it has the strongest ionization energy. More energy is needed because of the valence electrons of silicon being attracted to the protons in silicon's nucleus. And you might be wondering, why is this 4 when earlier we said 16? This is because the radius is going to be in the particular group, the particular row. So we're going to simplify it down to about 4ke squared. And you're also maybe curious as to why it says k. K is going to be a constant, and it has no effect in this. In AP chemistry, we don't need to worry about k. It's just a constant that's used in Coulomb's law. And if you're studying AP physics, I think it should be 1/4 pi epsilon 0. Although I can't remember if that's the correct equation. But don't worry about k too much. The idea here is that we have a higher attraction between silicon and the valence electrons and the nucleus. In silicon, then aluminium, and then magnesium is going to be the least. So this means that the ionization energies are going to be higher for those smaller radii. And here's a lovely example of this here, where we say that as you go along the group, as you go from the row of hydrogen to helium, it's going to increase. As we go from lithium to beryllium, it's going to increase. Sodium to magnesium, potassium to calcium is increasing. The ionization energy, because there's a force of attraction which is larger. There is a small discrepancy here and here, here and here, here and here. This is something I'm going to discuss in orbital mechanics, which is going to be the coming few classes. But for now, all we need to know is that the ionization energy increases as we're going up the periodic table and to the right. And again, this discrepancy, or I should say discontinuity, is present here. So we have a couple of discontinuities here and here. The most obvious of which is going to be between 2 and 13. As I said earlier, we say that 13 is going to be the start of those metalloids, which is going to be here and here and here, and this is due to the distribution of the electrons. In specific, if you want to pre-read about this, it's how electrons are distributed. So it's the distribution of electrons. So electrons, as they're put into orbitals, which we'll learn about, s orbitals and p orbitals, as they're put in, they're supposed to be put in equally into the things. However, when we have one orbital which has had a full set of electrons, which is 2, it becomes more stable. So we're going to have a lower ionization energy. So the atom gains stability after having a full s orbital and an empty p orbital. I will explain this in a bit more detail during the electron configuration classes. But for now, don't panic too much if you're seeing this and you're wondering, why is there a difference here and here, a difference here and here, here and here, here and here. I'll explain the two discontinuities in a bit more detail later on in the class. Alright, so let's have a look at this question here. The valence electrons are going to be the outer electrons of both sodium and magnesium, and they're both in the third energy level. Which atom is going to be, this is n equals 3, which atom, Na or Mg, experiences a greater force of attraction between a nucleus and the valence electrons? Really important we say valence electrons here. Justify your answer in terms of Coulomb's law. So in terms of our periodic table, we can have a look at sodium and say it's on row 3, and it's going to have, let's start off with sodium. Na has 1 valence electron. And magnesium has 2 valence electrons. I could write a sentence about this, but I think it's easier to explain, isn't it? So if we have 1 valence electron, we have Q times by Q divided by R squared, which is proportional to F, is going to be for, let's say this is for Na, gives a force of F. For Mg, we have 2 valence electrons, and we have two protons in which are unshielded, which is going to be proportional to 4F. And you can put K in there if you want to. And this gives us 4F. Therefore, we can say that 4F is going to be larger than F by a factor of 4. In this case, if we have a larger larger force of attraction, more energy is needed to separate electron. Sorry, I'll move this across here. From atom. Okay, so more force is needed to remove that. And this is just by looking at this. In fact, in AP chemistry, we don't need to do the maths unless asked to, but we can just reference Coulomb's law and say that this has been demonstrated by the proportion between the force and the outer electrons, the valence electrons, and the protons, which are unshielded, the available protons. And we can just say, we do need to mention in AP that sodium has 1 valence electron and magnesium has 2 valence electrons. Similarly, for the second question here, the valence electron of Na is in the third, so this one's going to be N equals 3, whereas the valence electron of K is in N equals 4. Which atom, N, A, or K, experiences a greater force of attraction? Well, in this case, we have Na is equal to, I don't know where I was going there. Na is going to have a higher force of attraction than Mg because of a smaller radius. As you know, F is going to be inversely proportional to the square of the radius. So if you increase the radius, you're going to decrease the force. Decreases the force because of this inverse square proportion. Okay. And finally, there's a couple more here. For this question, we're asking about the difference between Na, Mg, and K in order of increasing ionization value. So Na is going to be here. I can just draw a small periodic table here, Mg, and we can also do K down here. So to start off with, I could say that Mg is going to have a higher ionization than K because there's a higher force of attraction. That's my mistake. Than Na because there's a greater force of attraction between its valence electrons and its protons. And then the second part is actually from the previous question, which said, is Na or K going to be bigger? And remember, we said that Na has... Oh, goodness me. Sorry, I didn't mean to drop my phone there. We said that Na has a... Oh, okay, we're back. So we said that Na has a force of attraction which is going to be less than K. So K is going to be small because it's got a larger radius. So this is going to be the lowest, which is K, and then we're going to have Na here, and then we're going to have Mg here. Last of all, this is a question where it might get a little bit confusing without any sort of guidance or any sort of understanding of numbers, because numbers can be a little bit confusing. One of the ways we can complete this question when we're asked about which one's most metallic in character is going to be... Sorry, my phone got cut off because of a memory issue there. The smallest first ionization energy, so the easiest to remove an atom. So looking at these numbers, the smallest first ionization energy is going to be this one here. And it's as easy as that. So the element which can lose an electron the most is the most metallic. In this case, it's going to be element 2. Identifying element 3 requires us to look at the ionization energies and where there's a large jump in the ionization energies. Because we know that ionization energies increase across the period, we can see here that in element 3, this one to this one, these are around about the same. However, from 1,450 to 7,730 is a large jump. So it's going to be a jump which is attributed to the second and third ionization energies. This is going to show us that these two are going to be valence electrons. So this one is a valence electron because it's relatively low to remove. This one's relatively low to remove as well. However, the third ionization energy is going to be very difficult because it's going to be in the inner core shell. So because 7,700 is so large, it has to be from a large shell. In this case, what we're going to do is that we're talking about the third period. So in the third period, this has to be in group 2 because it has 1 valence electron, 2 valence electron. The element with 2 valence electrons in the third period is in the second group, and that's going to be magnesium, which is Mg. Similarly, for question D, we see what is the expected oxidation state for the most common ion of element 2. And we can see again we have one valence electron there because we have a huge jump, which is tenfold almost, from 496 to 4560. This shows us that, again, this valence electron is easy to remove. This one's going to be from the inner shell, so it's going to be harder to remove it, and that's from Coulomb's law there. The expected oxidation state is going to therefore be, if there's just one valence electron, it's going to be +1. And that leads us on to the last question. If there's only one valence electron, well, it's going to be in group 1. So the only possible answer is going to be Na, which is sodium, because it's in group 1 and it's in row 3. Okay, so don't worry too much about the coming classes. We're going to talk about quantum numbers. This time I'm not going to talk about it because I'm going to go through this in class. However, I hope you found this quite useful. Quantum numbers are a little bit more difficult in a way. I'll put in a couple more practice questions perhaps next week, and please do let me know if you have any questions. Sorry about the couple of mistakes on the PPT. I was just writing them and I didn't quite make it correct there in some places. But if you found this useful, please let me know, and hopefully in future, if you want something similar, then we can do this. We can do something similar again. Thanks for watching. Bye bye.